Hello, and welcome to our very first encounter with the heat equation. Our goal is to determine all real-valued solutions U that depend on x and t to the heat equation, which we will cast as ut equals uxx, of the product form u of xt equals capital X of x times capital T of t. As always with product solutions, we figure out all the derivatives that we need in the problem. So we have ut equals capital X of x times capital T prime of t. First x derivative ux is capital X prime of x times capital T of t. Second x derivative uxx is capital X double prime of x times capital T of t. So we'll plug all those derivatives into our heat equation. And we have ut equals uxx if and only if x of x, big T of prime of t, equals big X double prime of x times big T of t. And as usual with product solutions, we rearrange this to read big T prime of t over big T of t equals big X double prime of x over big X of x. So we have all our t's on one side, all our x's on the other side. And then, since this has to hold for all x and t, we know there must be a constant lambda in the reals with capital T prime of t over capital T of t equal to lambda for all t. We're only interested in real-valued solutions, so we're only taking lambda in the reals. And likewise, we need capital X double prime of x over capital X of x equal to lambda for all x. So we immediately decouple two differential equations, one for capital T, one for capital X, which we will now solve. So let's solve capital T prime of t over capital T of t equals lambda. That becomes capital T prime of t equals lambda capital T of t. This we know has the solution capital T of t is c e to the lambda t for some constant c. And the x equation, capital X double prime of x over capital X of x equals lambda. That rearranges into the equation capital X double prime of x equals lambda times capital X of x. And this is a second order equation, and we could put everything on the left side as capital X double prime of x minus lambda capital X of x equals 0. And we have to consider cases on lambda. So lambda is a real number, and depending on whether lambda is positive, negative, or 0, our experience teaches us that we are going to have different solutions to this second order equation. So let's first consider the case of a negative lambda. Lambda is less than 0. It will be convenient in problems like this, when we split up into cases on a parameter, whether the parameter is negative, 0, or positive, to write lambda as lambda equals minus alpha squared with alpha greater than 0. Just a nice factoring. Trust me, this is a good thing to do, and you'll see us do it frequently. So the x ODE is capital X double prime minus lambda capital X equals 0, or if you like, capital X double prime plus alpha squared capital X equals 0. And writing the ODE this way, with the alpha squared, makes it, I hope, very obvious that a solution is capital X of x equals c1 cosine of alpha x plus c2 sine of alpha x. And you'll note that, contrary to how I often like working with the complex exponential, I know from the start of this problem that I want real-valued solutions. I'm working with the heat equation. It models something that should be real-valued since temperature is real-valued. So I'm automatically going to my trig solutions cosine and sine rather than to complex exponentials. So this is my solution to the x ODE for lambda negative. Then what's the full product solution? Because I don't just have an x ODE to worry about. I know u of xt is capital X of x times capital T of t. So that is c e to the minus alpha squared t times the quantity c1 cosine of alpha x plus c2 sine of alpha x. At the top of the screen, we see that the solution for t is capital T of t is c e to the lambda t, but here lambda is minus alpha squared, so I'm writing everything now in terms of alpha. And I can clean up this expression a little bit. Let's multiply through by capital C, by that constant. So I get u of xt equals e to the minus alpha squared t, and now I'll multiply capital C times c1 and turn that into a new constant c1 tilde. So I have c1 tilde cosine of x plus c2 tilde sine of alpha x. As we saw in some of our discussions on the last transport equation, if I have an arbitrary capital C times an arbitrary lowercase c1, that's just going to be some arbitrary constant, so I'll write it as c1 tilde. And it's nicer not to have three arbitrary constants, just the two that I really have. So this handles the case lambda is less than 0. What happens if lambda equals 0? Let's just move along the number line. Then in this case, my x ODE is x double prime equals 0. So that means that capital X of x is c1 times x plus c2 for some constants c1 and c2. Very simple linear solution. Then I go back to the product solution. U of xt is capital X of x times capital T of t. And that's a constant c times e to the 0 times t times c1x plus c2. So the exponential is completely gone. I have a capital C times c1x plus c2. And again, I don't really have three free parameters here, c, c1, c2. I multiply that big C on c1 and c2, and I find that u is ultimately c1 tilde x plus c2 tilde for some new constants c1 tilde and c2 tilde. And now let's look at the case lambda is greater than 0. Lambda is positive. So it'll be convenient for me to write lambda equals alpha squared with alpha positive. And then the x ODE is big X double prime minus alpha squared big X equals 0. Alpha is positive, so this tells me from ODE theory that big X of x is c1 e to the alpha x plus c2 e to the minus alpha x. And since alpha is positive, these are real exponentials. There's no Euler's formula lurking about. So I go back to my product solution. U of xt is big X of x times big T of t, and that's a constant c times e to the alpha squared t times the quantity c1 e to the alpha x plus c2 e to the minus alpha x. Although I don't have the big T solution on this slide, we remember that it was e to the lambda t. Lambda is now alpha squared, so I've gotten rid of lambda entirely. And once again, I'll distribute my big C over C1 and C2. So my solution is e to the alpha squared t times C1 tilde e to the alpha x plus C2 tilde e to the minus alpha x. And these were all my three cases for the parameter lambda, negative, 0, and positive, and I got three rather different product solutions.